Let's solve LeetCode 155 min stack. We want to design a stack that supports push, pop, top, and retrieving the minimum element in constant time. Implement the min stack class. Min stack initializes the stack object. This is the constructor. Void push int val pushes the element value onto the stack. Void pop removes the element on top of the stack. Top gets the top element of the stack. Get min retrieves the minimum element in the stack, and we must implement a solution with O of 1 time complexity for each of these functions. Now, let's take an example and then we can think about how to do this and what the bottleneck is. So first we go ahead and initialize min stack. Okay, then we push -2, then we push 0, then we push -3, then we get the minimum value till now, and the answer is -3. After that, we pop out of this min stack. So -3 gets popped out. Then we retrieve the topmost element, which is 0. Then we get the minimum element, which is -2. I'm not diving deeper into this because we all know how stacks work. So let's get to the core problem. So initializing the stack object, this should be O of 1. Pushing the element value onto the stack, this should be O of 1 because all we need to do is append to the array because stack is just an array. We want to remove the element on top of the stack. That's also O of 1, right? So what we want to do is the last element, we have to remove that off. Then in top gets the top element of the stack. So we just have to access the element at the last index and then retrieving the minimum element in the stack. Now we know if we want to find the minimum of any array, that is going to cost us O of n time complexity. So this is the only operation that will give us O of n time complexity. Everything else is simply O of 1. So how do we optimize this process? Well, we want to get the minimum value, right? So what I can do is maintain an array which contains all of the elements of the stack. And then I can also maintain the minimum value overall, correct? So what I can do is -2 is there. So as of now, my minimum value is -2. Then 0, still -2, -3, still -2. Then we get the minimum value. We get -3. By the way, here the minimum gets updated to -3. Then we get minimum, which is -3. We pop off. But if we pop off, what is our minimum element going to be? We have to recalculate what our minimum element is going to be. How do we solve that issue? Right? So this is what we want to figure out. So what I like to do is just create a temporary stack here, which will help us visualize. So let's say this is our stack. The elements are -2, then we have 0, then we have -3, then we have, let's say, get minimum is done. So when we get minimum, -3 is returned because we have created a variable min value, right? Which contained the value -3. And then we pop off this -3. If we pop off this -3, this min value also is kind of deprecated because we have to recalculate this min value. And then we'll again have to do, hey, let's recalculate the entire minimum value of this stack. And that will cost us, in the worst case scenario, O of n again. And we don't want to do that. Well, what can we do? The bottleneck is that we don't have one element. So here we only have one element that we are going to keep track of as the minimum value. So as soon as this value that we depend on for being the minimum value is popped off, we don't have any backward operation. So that means it doesn't give us any fallback value. So what we want is, what is the value going to be if -3 is popped off? Well, it's going to be -2. And what if -2 is popped off? Well, then there's not going to be a minimum value because if this is removed, we are at the end. Correct? Let's take a little more example. So let's say we have -4, -5, and then we have -10. Okay, so this is our stack. The minimum value is -10. What if -10 is popped off? In that case, the minimum value will be -5. What will happen if -5 is popped off? We'll have -4. What if we have -4 popped off? It will be -3. What if -3 is popped off? It's going to be -2. And if 0 is popped off, it's still going to be -2, and then -2 is popped off, so we don't have a minimum value anymore. So it's just going to return an empty thing. So what have we done here? For each of the indexes that is present, we have created the minimum value we've seen so far, right? So when we start, -2 is the minimum value. Then we go to 0. 0 is greater than -2, so still -2 is the smallest value we've seen. Then -3 comes along, -3 is the smallest value we've seen so far, and so on. So what we need to do is, in addition to maintaining a stack, an array that just contains a stack, we're also going to maintain an array which is going to be another stack which contains the minimum values. And then when we need to pop off, we'll pop off from this minimum stack. For example, if -10 is popped off, we have to pop off from this -10, and we also need to pop off from this -10, right? From the main stack and from the min stack. If -5 is popped off, we'll cut it over here. And whenever get min is called, we'll just look at the topmost value over here. And if top is called, we'll look at the value over here. Because, well, why would we look at the top value of min stack if you want to find out the topmost element of the main stack, correct? So fairly easy. This is just a realization that we needed to have. So let's go ahead and create a stack which is going to be empty initially. Then we also have the min stack, which is also going to be empty initially. Cool. Because the reason for this is because min stack is not taking any arguments through the constructor. If there was, we would have to initialize, and that would mean we would sacrifice O of one-time complexity, because we do need to find out what will be the minimum element so far. Okay. Let's go ahead and implement the push operation now. How do we push? So as I said, it's very easy, self.stack.append, and then we'll just append the value, correct? Now we also need to append to the min stack, right? So we'll just do self.stack or minstack.append, and we'll just append the value. But will we just append the value? No. What we'll do is find out the minimum of value and the last element that is present in min stack. So we have min stack at -1 being used here. Why am I doing this? That's because, let's say I'm appending -5. Okay, so I want to find out the minimum value between -5, the new value that I'm trying to add, and the previous topmost value, which will give me the previous minimum value in the stack so far. So we want to ensure that we have the biggest minimum value, right? Like the smallest value. So we'll just compare with the topmost value here, because the topmost value will always give us the least element, the smallest element. So there we go. And now if you're doing min stack at -1, we also need to ensure that minimum stack exists. So what we can do is, hey, if self.minstack exists, in that case, we are going to do this. And if it does not exist, in that case, we will just do self.minstack.append, and then we'll just append the value. Cool. Now, another thing to keep in mind here is we need to do self.minstack. Cool. So it takes the topmost element, compares it with value if the min stack is not empty. Okay. And if it is empty, in that case, we'll just append to the min stack directly. Now, if we want to pop off, how do we do? Well, we know that we are essentially having an index for each one of them. So -10 will correspond to -10 here. So if -10 is at index 5 here, it will be at index 5 in this one. So what I can do is self.stack.pop. Then I can also do self.minstack.pop. And yeah, that's basically it. Now I've not put any condition of checking that, hey, if the pop is called correctly or not. So the reason for that is methods pop, top, and get min operations will always be called on non-empty stacks. But push can be called on non-empty stack because initially it's going to be an empty stack. We want to append to it, correct? Now let's go ahead and find the topmost element. So the topmost element is going to be return self.top, and we just, not top, sorry, self.stack, and we return the -1. So just the top of this tower, the stack that we have the last element in there. And get min. How do we find out get minimum? Well, easy. We've created an array minimum stack for this particular thing. And we call the -1 on that because it will always give us the least value. It is guaranteed by this line that we've put in. Cool. Now let's go ahead and run this and see if that works. It does accept. Let's go and submit. And it is accepted. So the time complexity of this is O(1) because that was basically our question. And the space complexity is O(n) because we have to maintain the main stack and we also have to maintain the min stack. So O(n).